welcome to this session. We have Miguel Romero, who's going to tell us about the complexity of general valued CSPs seen from the other side.
Okay. Okay. Thank you, and thanks for coming. And yeah, I mean, this is John work with Clement Carbonell and Standard Sydney, and this work is about the general value constraint satisfaction problem, or VCSP, which is a general framework to express decision and optimization problems, and the combination of both. And there are several ways of formalizing this problem. We choose one that is based on what we call valued structure, which is as follows, okay? So a signature sigma is a set of function symbols, each of which has a fixed additive Rf, F, where F is one of the symbols. A valued structure A over sigma consists of a universe A, which is going to be finite. And we have interpretations for each of the possible symbols, F, right? And one interpretation will map all the tuples of the same additive of F to a value, right? Which is a non-negative rational or infinity. And for two valued structures A and B over the same signature sigma, the cost of an assignment H from A to B is defined as follows: is the sum over all the possible symbols in sigma and all possible tuples of the same additive of the contribution of that tuple, right? And this is the weight of the tuple in A times the weight that we obtain in B by mapping the tuple with H, right? So this is the cost. And the definition of the problem is we have two valued structure A and B over the same signature, and the goal is to compute the optimum of A and B, which is the minimum cost over all possible assignments, right? So this is the VCSP. And well, there are many particular cases of this problem. The first one is the CSP itself, right? In the CSP, we want to satisfy all constraints simultaneously, which is the same as asking for the existence of a homomorphism from a relational structure A to a relational structure B. And to encode this problem, we just can use zero infinity valued structures, right? It's not very difficult. Similarly, we can encode the min CSP, where we want to minimize the unsatisfied constraint by using 0, 1 valued structures, okay? And another particular case is the finite value CSP, where there is no infinity. We just have finite values. And in this case, the problem is just optimization, right? Sorry, we don't have feasibility problems, right? So there are many particular cases, okay? And of course, the problem is hard, it's simply hard, so it is natural to look for tractable restrictions. And here there are two main lines of work. The first one is non-uniform restriction, where we fix the right-hand side structure B to be fixed. And in that case, the situation is very clear. In particular, the last year, the CSP dichotomy conjecture was proved. And the other line is structural restrictions, where we restrict the left-hand side of A, of the problem. And this belongs to a class C, okay? And this is the focus of this paper, okay? And in this case, for CSP and the case of bondedarity, the situation also is very clear. And it means that we just look classes of bondedarity where the additive of all the relations we see in the structure, in the class, is bounded by some constant, right? So that case is clear. And for the general case, it's not that clear, but at least there is a classification for fixed parameter tractability. So, and for the case of VCSP, it is not that clear, okay? And that's the main motivation of this work, right? And we will focus on the case of bondedarity. So the main question is, for which classes C of bondedarity is VCSP of C tractable, okay? That's the main question. And, sorry. Our main contribution is a characterization of the tractable structural restrictions for VCSP in the case of bondedarity. And then what we have is that all the tractable cases are solved by a particular method, which is the Cherali-Adams hierarchy. So then the second contribution is a characterization of the power of these methods in terms of the left-hand side structure A, okay? We will see later, okay? Okay, so now I will talk a bit about the case of CSP, then I will give you the characterization of the tractable structure, then I will talk about Cherali-Adams, and finally I will conclude with some open questions, okay? Okay, so one of the first tractable restrictions for CSP is that of bounded tree width, okay? And we have that the CSP of C is in P time if the tree width of the class is bounded, right? And this was extended later in the following way. So we say that, okay, we have A and A prime, these are relational structure. We said that they are homomorphically equivalent if we have homomorphism in both directions. And then we define the tree width modulo homomorphic equivalence of A to be the minimum tree width over all A prime that is equivalent to A, right? So of course, this quantity is going to be smaller than the tree width. And also it is known that this quantity is realized in a particular structure, which is the core of A. And the core is the minimal substructure of A that is equivalent to A, right? And it is known that it exists and it is unique. So we have that this quantity is precisely the tree width of the core of A, okay? And what we have is that the CSP of C is in P time even when the tree width modulo homomorphic equivalence of C is bounded, okay? Then we have a matching hardness result with respect to parameterized complexity in the case of boundedarity that says that when the tree width modulo homomorphic equivalence is unbounded, then this problem is hard, right? Is W1 hard. And the problem that we consider is a parameterization with respect to the size of A, which is the left-hand side structure. And the proof is a reduction from the parameterized version of clique, which is a well-known problem that is hard for W1. It's complete, actually. Okay? So if we put this together, we obtain a complete classification, right? So 1 implies 2 is trivial, 2 implies 3 is by Gross Hardness, and 3 implies 1 is Dalmau, Colitis, and Barty, okay? So we would like to have something like this for the case of BCSP. That's the goal. Okay, okay, so let's see. So, well, in the case of BCSP, we also have that tree width is tractable. I mean, BCSP of C is going to be in P time when the tree width of C is bounded. And now we need to be more precise because how do we measure the tree width of a valued structure, A, right? And, well, we look on the tuples, and we just look the tuples with positive cost, right? Because if you have 0 cost, it's like you are irrelevant for the problem, right? So, so then the tree width of a valued structure A is going to be the tree width of the positive part of A, which is going to be the relational structure given by all the tuples with positive cost, right? That we call pos of A. Right? So this is the way we measure the tree width for a valued structure A. And, right. And our first observation is that we can go beyond tree width, actually. So here is a very simple example. It was supposed to be an animation, but so the signature, we have 2 symbols. One is binary, the other is unary, okay? We have this structure A2, okay? The arrows represent the interpretation of the binary symbol, and the value there is infinity, which means that is like a hard constraint, right? And the interpretation of mu is just 1 in all the nodes, right? So suppose that we want to solve this problem over B, which is a right-hand side structure. So basically the goal is to find a homomorphism so that the cost in all the nodes is minimum, right? So what we can do is just, okay, it's kind of clear that we can identify these two blue nodes, right? Because one of the two costs is going to be smaller anyway, and we have this symmetry in the structure, right? So we just can identify it, and what we get is that solving A2 over B is equivalent to just solving this path over B, okay? And this same reasoning worked for all possible grid, right? Size 3. In the case of 3, it's going to be something like that, right? And we have this for all possible grid. So if we consider the class of all the grids, the tree width is going to be unbounded, right? Because it's the tree width of the grids. But it's going to be in p time because it's the same as solving this path which it has bounded tree width. And we know that it's tractable, okay? So this is an example that we can go beyond tree width. So at this moment, the picture is something like this, right? We know that bounded tree width is in p time. We know that beyond bounded tree width modulo homomorphic equivalence is hard, because in that case, even CSP is hard. So PCSP is also hard there. And the frontier is somewhere in the middle, right? And clearly, it's going to be related with tree width, right? But the goal here is to try to find precisely what is the limit, okay? And the idea, as in the previous example, is to just introduce a new notion of equivalence that is more suitable for BCSP, right? And this notion is as follows. We say that A and A prime over the same signature sigma are valued equivalent if the optimum is precisely the same for all right-hand side structure B, independently of B, okay? So this is the notion of valued equivalence. And this is the main classification, the main theorem that says that BCSP is going to be in P time if and only if is FPT, if and only if the tree width module valued equivalence of C is bounded, okay? And again, 1 implies 2 is going to be trivial, 3 implies 1. There we use Cherry Adams. I will talk about this later. And 2 implies 3 is a combination of Groe's proof and some new tools. And the problem here is that in the reduction of Groe, we need the notion of core. It's very important to encode click, but here we don't have the notion of core. So what we did is that we provide a characterization of valued equivalence in terms of some type of homomorphism, and this that is called inverse fractional homomorphism. And with this, we can define a notion of valued core. And we can use it in combination of the reduction of Groes to prove the hardness. Okay? So this is the idea of the proof, right? Some comments. If we apply this to zero infinity structures, we obtain Groes classification. And also, it follows from the proof that this classification also works for finite value structures. Okay? So this is the final map. And the last comment is that, okay, we know that the boundary is strictly above bounded tree width and strictly below bounded tree width modulo equivalence. We know that these two notions are different. We have some separating examples. So it's in the middle, okay? Okay, so finally, Cherry Adams. So, okay, we can easily write an integer linear program for an instance of the BCSP. The basic LP is going to be the relaxation of this one, and in general, it's not going to be tight, okay? And this is going to be the first level of Cherry Adams. And just let me mention that we have two types of variables in this program. We have variables associated to pairs of X in A and D in B, and some other variables associated to partial mapping from A to B, where the domain is a scope, okay? And a scope, it means that these are all the variables that appear in a positive constraint of A, okay? And in the K level, we have precisely the same, but now we consider more variables, and in the first type of variables, now we consider all the mappings whose domain is X, where the size of X is at most K, okay? And it is a folklore result that if the tree weight of A is at most K minus 1, then the K level of Gerali-Adams is tight for A. And it means that for all B, independently of B, the K level is tight for AB, okay? And the goal here is to try to understand the limits of this. And let me give you the final theorem, which is as follows. So, okay, we have the following. We fix K, okay? We have A to be a valued structure, and A prime is going to be its core, okay? And we have that the following are equivalent. The K level of Gerali-Adams is tight for A, if and only if the tree-width modulo scope of A is at most K minus 1, and the overlap of A is at most K. So let me explain this a bit. So in the tree-width modulo scope, we look three compositions, but now we can have some bugs that are very large, but if they are scope, we just ignore these bugs, right? So in the definition, we just look three composition, and we measure the width just of all the bugs that are not scope, okay? So this measure is going to be smaller than tree width, right? So this is the definition of tree width modulo scope, and why and how it is connected with Gerali-Adams and why it is useful. The high-level idea is that to show tightness, we need that for each bug to have some variables associated that are in the program. And remember that in the program, we have these two types of variables, right? The one that the domain was some scope, and the other, the domain was some X with size at most K, okay? So this is why we need to consider this type of decomposition. And also to show tightness, we need that the intersection of every pair of scope is at most K. And this is the second condition, that the overlap of A is at most K, right? And for the necessity part, we combine some results on the power of K consistency for CSP with our tools of valued constraint and fractional homomorphism, okay? Okay, so finally, some open question about the tarity. It is not clear what happened there. Also, the case of min CSP and max CSP, the hardness proof in the characterization, we need rational numbers there. So it does not apply for min CSP. And actually, we note that in that case, we can go beyond bounded tree with modulo value equivalence. So, but we don't know what is the boundary. And the same for approximation. We know that if we consider constant factor approximation, we can go beyond bounded tree with modulo value equivalence, but we don't know precisely what is the boundary. So that's it. Thank you.
Time for a quick one or two questions. Okay, let's thank the speaker again.
Thank you.